Hello students, welcome to our Mechanics of Materials online lecture, and today we will be going to start a new chapter. It's called bending, and in this class I will teach what is beam, different types of beam, and how to develop shear and bending moment diagram. Now bending, so bending is associated with bending is associated with beam. Now let me define beam. A member which has following two characteristics is known bending is known beam, sorry, is known. So what are the characteristics? One, the member should be slender, and number two, the member should support loading that are perpendicular to its longitudinal axis. So if I draw a slender member and this is the longitudinal axis, then the load on this member, this is load, and these loads and the axis, the angle is 90 degree. Now as I said, so there are a member, if the member is slender and if the member supports loading that are perpendicular to its longitudinal axis, we call this member a beam. Now beams are classified beams are classified as to how they are supported. So the first one, the first case is, consider a beam one end is a ball support, roller support, the other end is a pin support, okay, or we can simplify this. We have this kind of support, okay. So this is called simply supported beam. So this is one example of simply supported. Another example is the same thing. We have two support at the two end and one load from the top. All these three are simply supported beam. Now now go to the next type. So if a beam is fixed at one end and free on the other end, this one these are the example of cantilever beam, okay, cantilever beam. Now if I take this first example, now it has a pin connection and the roller support. If I extend this beam, so this portion is overhanged, and the another example is the same, support here and support here, but this portion is overhang. Then this example or this type of beam is known as number 2 overhanging beam. So these are the three types of beam. The first is this simply supported beam, where the both end of the beams are raised, has a support. Cantilever beam is one end is fixed, and the third one is overhanging beam, where a significant portion of the beam is overhanged. So there is another classifications of the beam, and this classification is based on the cross-sectional area of the beam. Now let's draw a simply supported beam where this one and another example, and there's another configuration of this. Say the cross section is different. Now here and here the cross section is the diameter, say D1, here also diameter is D1. Okay, say D2. So all the diameter throughout the entire section is same. So D1 equal to D2. So this type of beam is called prismatic beam. In the prismatic beam, the cross section of the beam, the cross sections of the beam are same throughout the beam. Throughout the beam length. It means the cross section at the beginning, at the center, at the end, or in every section. If we take the cross section, all the cross section, if it is circular beam, diameter should be same. And the another type is called non-prismatic beam. In non-prismatic beam, the cross section of the beam are not same. Throughout its length. So for example, if that in the cross section is a circular diameter beam, if it is a D1 and it is a D2, then D2 is D1. So they are not the same. D2 and D1 are not the same. So that's why it is called non-prismatic beam. Now let's see, and the next topic we are going to discuss is pure bending. Pure bending. I want to show you one example here. So as you see, this athlete lifting is lifts a weight bar. Okay, now this weight bar, there are two weights at the two end, and he holds the bar here and here in two different locations. So if I draw this in 2D, if I draw this in 2D, okay. Okay. Now let's assume this 80 pound, these mass are 80 pound of each, and the distance where he holds the bar with his hand, the distance between two holding is 26 inch. Okay. And this distance is 12 inch. This distance is 12 inch. Okay, now let's draw a free body diagram of this loading condition. So I am considering only this length. So this is 80 pound, and so this point is D, this point is C, this is A, and this is B. 26 inch, and here. Now this is the reaction force RD, which is 80 pound, and this is RC, which is also 80 pound. Now this 80 pound load from the top, actually from the top, but these two reaction forces RC and RD, these two support actually holding or withstanding these 80 pound 80 160 pound of load. And this is 12 inch, this is 12 inch. So if I take this segment, if I take this segment, CD segment, I take this CD segment, now in the CD segment, the moment here is 80 multiplied by 12 inch equal to 960 pound inch, and here the moment here C M also 80 multiplied by 12 pound inch, 960 pound inch. Let me draw this again. M. Okay. So as you see, the both end and D and C, the M is 960 pound inch, 960 pound inch. Both the moment are equal. So if in a beam the applied loading creates if the beam in the applied load creates a moment, if in a beam, if the applied loading creates a moment which are equal but opposite in direction, then that beam is subject to pure bending. So let me repeat again. If the loading condition of a beam is such that the bending moment are opposite, the equal but opposite in direction, for in this case this one is counterclockwise, the moment at D is counterclockwise, but moment at C are clockwise. Both have the same value, 960 pound inch, but opposite in direction. So then we can say that beam is experiencing a pure bending. Now When we apply load to a member in a beam, there are so the applied loading in a beam. Let's take an example. A beam has a pin support at one end and triangular distributed load other end and one end, and roller support at point C, pin support at point B, and triangular distributed load up to point B, and the point load at point D. Okay, so there are couple of different types of load here. One is the point load, P, linearly distributed load, triangular distributed load W naught, and there are reaction forces at point A and on point C. And because of this applied loading, the applied loadings on the beam creates one bending moment, as we have seen in the previous example, and also it creates internal shear force. And both the bending moment and internal shear force vary from point to point. For example, the shear force and bending moment are not the same throughout this entire beam. It may be minimum, there might be the bending moment and also the shear force are maximum at certain point and minimum at certain point, but each point has their own values. So in order to design a beam, we need to know the maximum shear force and bending moment. So one way to find this maximum bending and bending moment and the shear force is by develop shear force and bending moment diagram. In the rest of the class, today's lecture, we will figure it out how to draw shear force and bending moment diagram of a beam. Now, to do that, first we need to know sign convention of the beam. And it is very important to know the sign convention of the beam, and you can also study this by yourself from the book, page 260. Okay. Now, so consider a beam which has arbitrarily distributed load, upward, another beam which has rectangular distributed load, upward, and triangular distributed load, upward. So all these three examples are examples of positive distributed load. On the other hand, this is the sign convention. On the other hand, if my load is downward, arbitrary, rectangle, triangular, these three are negative distributed loads. These are the example of it. So if the direction of the arrow is upward, then it's a positive, and if it is downward, then it is a negative. So these are the example of this is the sign convention of distributed load. Okay. Now the next is internal shear force. What is the sign convention of internal shear force? What is the sign convention of internal shear force? Now, if my beam, so if this is a internal shear force, this is a internal shear force. Okay. And I need to assume this. Now, if the internal shear, because of this internal shear force, if the internal shear force creates clockwise rotation of the beam, then this internal shear force is positive. Okay, if the internal shear force creates a clockwise, for example, it will create a clockwise rotation with respect to this point, it will create a clockwise rotation of the beam, then this internal shear force is positive. I'm giving another example. Say now the internal shear force is in the left hand side, but you are taking a moment with respect to a point here, now it is still rotating clockwise, so this one is still a positive internal shear force. I stands internal, S stands shear, F stands force. Okay. However, if is downward, this internal shear force is downward, and okay, I think I made a mistake here. Okay. Let me hold on. I want to check something. Yeah, I think I made a mistake here. So this one is going to be downward. Okay, and it creates let me draw say this again. So internal shear force, if the beam has shear force and this is the direction of one side and this is internal shear force ISF, internal shear force, and if I take a moment with respect to, if I consider this is my point and it rotates with respect to that point, is a clockwise rotation, then this ISF is positive shear force. And if this case the shear force at the other phase, its direction is upward and it is fixed, if I take a moment with respect to that point, if it is rotated in that direction, this is also ISF, internal shear force, and it also creates a clockwise rotation, and this is a positive shear force. Okay, now again, if this shear force is, this is an ISF, is that direction, and it is creates a counter clockwise rotation, then this ISF is negative shear force. Okay, sorry for the confusion. This is please also read the page number 260 of the book. Now the third sign convention is moment. Third sign convention for internal moment. So the first case, let's consider this one. Okay, a beam, and it has an internal moment m, and because of this internal moment the beam is bending in such a way that top fiber, experiences compression, then this moment is positive. I'm repeating, if the moment in such a way, such a direction, clockwise or counterclockwise, it doesn't matter. If moment creates, if the moment, if the beam bends due to the moment, and the top fiber experiences the compression, then this moment is positive. So this is one example. Now again, this is another beam, and this is this is top, this is bottom, this is top, this is bottom. Okay, and also this top fiber experiences compression. So this moment, this m, is positive. Now we have a moment like that, and the beam bent like that. Okay, now this top fiber experiences tension, and that's why this moment is negative. I hope I was able to explain this sign convention, and the next thing is we are going to solve a example problem, and that is problem number 6.1, page 262. Okay, so in this problem so this is the problem, example 6.1 actually in the book. So in this problem, a simply supported beam has a distribution load W. Okay, we need to find we need to draw the shear force and bending moment diagram. Okay, now let's draw this beam. Say A, B. It has pin connection at A. It has roller support at B. Okay, and distributed load W. Now I can draw the free body diagram of this setup. So this is my A, Y, this is my B, Y, and this is my A, X, and this is W. Now as you remember, we previously learned that in order to find the reaction forces or solve the problem, we need to convert the distributed load to a point load. So if we convert the distributed load to a point load, so we can further simplify this loading condition. We can write, and this is L. Okay, this is AX, AY, BY, and we know this is WL, this point load, and this point load is located from the point A. From the point A, this WL is W by 2 length away. Now if I take the moment with respect to A, we can say By multiplied by L is equal to WL multiplied by L by 2. We can say By equal to WL by 2. If we take the moment with respect to B equal to 0, we can say AY multiplied by L equal to WL multiplied by L by 2. So AY WL by 2. Okay. So we got the reaction forces. Okay. So this is WL by 2. This is WL by 2 because these are AY is equal to WL by 2, BY is equal to WL by 2. Okay. Now, and this is the length L. Now, to draw bending moment and shear force diagram, we actually do not need any longitudinal force. We do not need any longitudinal force, like we only need perpendicular force. So that's why we can ignore AX. We can ignore AX. Okay. So this W. Actually, you don't need to go all these steps. If this is a symmetric loading condition, if your distributed load is W, your reaction forces at the both end, if it is a simply supported beam, it is actually WL by 2. Understand? If it is a distributed load with W, then if it is a simply supported beam, the reaction forces are WL by 2, because your point load, to convert your distributed load to a point load, is equal to W multiplied by L, and these reaction forces actually supported this point load, and each of the point load is actually the half of the point load. Okay, now the next we will develop to draw a shear and moment diagram, shear force and moment diagram. We need shear and moment function. Okay, to derive a shear and moment function, we will cut a segment from the beam, and this segment, say we cut a segment. Okay, so we cut a segment at point C. Okay, so now A, C, and this segment has a distance X. This segment length is X. Okay, now if we convert simplify this one. Now this one we need to convert this distributed load to a point load. This is Wx and this length is this load here we have a load actually WL by 2. Okay, WL by 2. This length is X and this is X by 2. As we know that when the rectangular load we convert to a point load, the location is the half of the length of the rectangle. Okay, now let's write the equilibrium equation summation of f y equal to 0. Okay, once we cut here, there are two things actually generate. This is my V. Okay, this is the shear force and the moment. The shear force and the moment. Okay. Now let's write the equilibrium equation summation of Fy equal to 0. Now WL by 2 is in the positive direction, and we have Wx in the negative direction and we have V in the negative direction, so it's going to be 0. So if I take the V, I can write W L by 2 minus X. So this is my equation number 1. Now take the moment with respect to point C equal to 0. WL by 2 multiplied by X. Wx multiplied by X by 2 plus M equal to 0. If I rearrange this equation, I can write W by 2 L X minus X square. So this is my equation number 2. Okay. Now let's draw the entire beam. Okay, now let's see, consider equation 1. V equal to W L by 2 minus X. Okay, at x is equal to 0, v is equal to what? WL by 2. At x is equal to L by 2, v is equal to WL by 2 minus L by 2. So v equal to 0. At x is equal to L, v is equal to W L by 2 minus L. So v is equal to minus WL by 2. Okay. So let's consider, let's draw the bending moment shear force diagram based on these three values. So this is my distributed load, this is my point load, okay, this is W. Okay, now I found V, this is V, is maximum is WL by 2. WL by 2. V is WL by 2 maximum, positive, and V, the negative maximum, is WL by 2. And at L is equal to L by 2, it is 0. So my bending moment, sorry, shear force diagram is like that. Okay. So now see that at x is equal to 0, here my x, this is my x is equal to 0, v is equal to WL by 2, at x is equal to L by 2, v is equal to 0 here, and at x is equal to L, v is equal to minus WL by 2. Okay. Now, so with those values, we were able to draw the shear force diagram. This is my shear force diagram. Okay. This is my shear force diagram. Now let's consider these equation number 2. Equation number 2. So M is, as you see, M is not a linear function like V. Okay. So how can we find the maximum value of M? What is the minimum value of M? So since M is a nonlinear, if is a nonlinear quadratic, so to find the maximum moment, we need to differentiate m with respect to x. Okay, then so the slope of m, derivative of m, is maximum when it is 0. So let's derivative the m. So m is equal to, so let's differentiate the m, w2 lx minus x squared. Okay, so dm dx going to be L minus twice x. Now at x equal to 0, now so this thing, so this is 0. Okay, so w, so L minus 2x equal to 0, because w by 2 cannot be 0, so x is equal to L by 2. So m, we will get maximum value of m at x equal to L by 2. So what is that value? So m w2 L by 2, if I plug the value of x here, minus L square, that gives us w L square 8. Okay, so this is L square by 4 actually, because x square, so is going to be, if I replace x square is equal to L by 2 square, that means L square by 4. So L square by 4, so that is w L square by 8. Now, so if I write, so the L m maximum is equal to w L square by 8. So at x equal to 0, m is what? We know m is equal to w2 L x minus x square. So at x is equal to 0, m is equal to 0, x 0. At x is equal to L, m is equal to w2 L minus L square. It is also 0. This is at x is equal to L by 2. So we got the three value of m at three different point of x. X is equal to L, x is equal to 0, and x is equal to L by 2. And if we draw the bending moment diagram, okay, so bending is going to be 0, okay, so this is m max, which is w L square by 8, and this is my moment. Okay, this is 0, this is 0. So this is my bending moment diagram. So please practice this problem and other example problems. For example problem 6.2, 6.3. Please practice example 6.2, 6.3, 6.4. And so the problem I solved, it is actually 6.1. So please solve the other problems of the book, and then you will know how to draw the shear force and bending shear force diagram and bending moment diagram. And this shear force diagram and bending moment diagram is very important, because this shear forces diagram and bending moment diagram, both the diagrams give us the maximum shear force. For example, in this case WL by 2 minus WL by 2, and maximum bending moment, this is WL square by 8. So that's all for today. We will continue our lectures on bending in the next class. Stay healthy and be safe. Thank you very much for your time and attention.